So we're in section 1.7 in your textbook. And so this is a section that really will be a foundational piece for, well, quite honestly, most all of how you'll apply mathematics. There's pure mathematics, there's applied mathematics, and modeling real world phenomena with equations is incredibly important and a skill that can become a big component of what you might do professionally. So I wish you good luck, and I hope you find it enjoyable. What we want is, my hope today, the learning objective is just to get you to want to move towards word problems. So word problems are something that we want to have a growth mindset with, something that we are going to cyclically, and as we apply the steps, we're going to do those steps multiple times. So there's multiple iterations in a in a modeling equation with from a word problem. So it's like a puzzle. And so what we want to do is just get you excited about this puzzle, and that's what we're looking for, because it's going to be here the whole rest of the year. So there's some good guidelines on page 65 in your text. Finding variables, and we'll expand on that, where words then come into equations, and then the idea of setting it up. And so I want to just expand on the variable. So we've got independent variable, and I'm going to put S. We're going to do single variable problems, but you could have multiple variables, and then dependent variables. So your inputs and your outputs is so fundamental to and necessary to be able to find and identify those. And often it comes not as the first step, but when you're looking at the words, and you might be doing this concurrently. So these three right here sort of keep going, and what we want to do is keep making sure that we're checking and rechecking. And once we know that we've set it up right, then it's time to go apply our equation solution tool belt. So all those tools that we have for how we solve those equations. But if we don't have the equations correct, then the answer, it goes back to that garbage in, garbage out. So we want to make sure we've got the right things going in so that the output makes sense. So our experience today will be by a breadth of examples. So in your textbook, talked about the interest. So I'm going to go over a couple quick principles and then a bunch of examples. So the interest paid, okay, that interest is going to be on some principal, and that principal, right, has some rate over time. And the most important thing here is that the rate times time, that rate has to be in the same units as the time. So if your rate is something per year, then your time would need to be in years. If it was per month, your time would need to be in months. And lots of fun interest problems. And what we're going to do, just setting up today, we're really dealing with just linear problems. And the fun of this is that those problems will become much more complex, and equations will be extend beyond this as we go through the textbook. So the first one here, Mary inherits $100,000, invests in two companies. She decides to invest it. One returns 6% and the other returns 4.5% each year. So in that 1 year, the total interest earned is, so in that first year, is 5,775, so $5,775 she gets back on her $100,000 investment. So how much was invested in each company? So we're looking at problems where the principal doesn't change here. So this is not like compounded interest, things like that. But so let's look at how we would think about what we're trying to model, what our variables are, and how we're going to come up with an equation here. So we kind of deconstruct this. We see that would be the output, right? That's what ends up coming out after a year. Right? That's the input, but it needs to be broken up into two pieces. So we can kind of think of it this way. We've got X that we're going to, we'll call that for company 1. We'll call it the 6% company. And Y for company 4.5%. And so we would know that X plus Y has to equal 100,000, which would lead us to, because we're going to need eventually we're going to plug this thing in and we're going to end up with one equation, but there would be, let's stop right there, that would be the first equation. And we know for our other equation, all right, we're going to have X times, we get 6% back from company X, plus Y times 0.045, and we know that's got to equal 5775. So what we actually have here is two equations, two unknowns, but what we're able to do, sort of nicely is just solve this equation for Y and plug it right into this equation. So we're solving what are called simultaneous equations, but I'm going to do it here by just substitution. We'll get into some other solution techniques on how to do this, but right, here's our two. X plus Y has to equal 100,000, and then the amount invested in company X, right, we end up with 6% back, plus the amount in company Y, right, the 4.5%, that has to equal 5775. So this one, we can just do this. We can solve for Y and substitute. So that's what you see going on below here. And then you just go ahead and, after a little bit of math, we come up with our solution for X. And if that's the solution for X, then we would also know that as we solve for it, that Y equals, right, 100,000. Ooh boy. 100,000 minus 85. Okay. Oops. And that came right from that equation right there when we solve for Y. So there could be, probably about 20 different sections in that textbook. We've got, other thing we're looking at is time needed to do a job comes up, and then the quintessential, distance, rate, time, two trains traveling, all that kind of stuff. So we will get into that. We're just trying to get ourselves able to approach these problems with an open mind and an ability to create equations. Like that's what we're doing, creating equations. And to do that, we need inputs and outputs. So if you don't get it in a problem the first time, just look at it again. Take a quick little break and then look at it again and take a look at what you did and see if it holds up. So our first example that we'll look at here is, you can go ahead and read that, and then we'll go through the solution of it. So we look and we see just kind of, obviously population comes up, and there's something about years, and we're asked about the population, right, getting to a number, or right down here actually we're told population at two different numbers. So in terms of variables, right, time is actually going to be the independent variable, and the dependent, the thing that we're calculating, you see it right here, predict the population. So that's going to be the dependent variable. Same thing here. Now we go back and identify the year. It's still the independent variable. We're just going to solve for it because here we would have the answer for the dependent variable. So let's go take a look and see how we do this mathematically. So the input, right, the dependent variable is time, and it's going to be years since 2004. Right, this is going to be relative, as if Time starts right there. That's the beginning of the problem in 2004. The output is population. And what we want is the population in 2013, which would be when time, t in years, is 9. And so the rate of change is people per year. So we're going to take the two pieces of information that were given to us, and we were given the population in 2009 and the population in 2004. So the rate change in this problem, these are all linear problems, and pretty much everything will be that way. And so we'll deal with different rates of change, but we'll just be doing linear pretty much today. So change in population over the change in time. So I'm going to just compute this. This would be 380 people per year. So the change between 2009 and 2004, people, and the change in time, the number of years. So the population at any time is equal to that rate that we just calculated, times the time, where the time is years, not the year, but number of years since 2004, plus P naught, where P naught is the population at the beginning, right? The population at 2004. So let's see what we've got here. Now, at this point, we've got it all set up. Now we just need to execute the numbers. So 2013 would be P9. So T is equal to 9, right? And that's the answer. When we plug it in here, we find P9 is equal to, we're about to find what the output is based on that input. 380 times 9 plus 6,200. I'm going to stay with our units. All right, units are going to be important. They also make sure that we have they help us. It's called dimensional analysis. When you track your units, so you see here years cancel, so we end up with people plus people. If we didn't end up with people plus people, we would know that we had made some sort of a mistake getting there. So it's very much a big help to track your units as you go through these problems. So we will do that. I'll make sure we get in the habit of doing that. So, and then the time in years when the population, the second part is 15,000. So in this case, we would know what the output is, right? 15,000. And what we're trying to solve for is t right there. So this is p at some t. I just don't know when, but I know its value. So that's 15,000 is equal to, oh, there's the same equation, we just don't know t. But now we go solve for t. So you see where all the solution techniques come in aggressively here. So we'll take a look at another problem here where Jamal is choosing between two rental companies. So we've got two things that are possible here. So we might need to compare. We might need to compare two different functions. So just think about that. The first is Keep On Trucking. Charges $20 up front and then 59 cents a mile. Careful of units here. This is in dollars, that's in cents at the moment. The second, Move It Your Way, charges an upfront of 16 and then 63 cents a mile. When will, at what mileage, when will it be a better choice? Where it will Keep On Trucking be a better choice? So these two, depending on how many miles you go, these two companies cost a different amount, but at some point it looks like they're going to cross and then they're going to flip. So I think a graph might be in order here shortly. So thinking about variables, all right, the variable input and the output. Input is D, like that's what drives this thing, right? The distance is what the input is. To find then, I'm going to call them K and M, where K is the cost for Keep On Trucking. M is the cost for Move It Your Way. So those are the two outputs. Both are dependent upon how many miles. So the upfront fee, you can think about that at mileage 0. So before any miles are put, you owe some money. For Keep It or Keep On Trucking, it's $20. For Move It, it's 16. Now the rate, right, this is some rate problems. So I use the idea of, I use M, like the slope, but the rate that's charged for keep it is 59 cents a mile. Notice I've changed units here to dollars, so $0.59, and there's the rate for move it. And so the functions, right? The functions for cost are going to be MKD plus K naught, right? Where that's keep it, or keep on. And then for company M, you have to use the other rate, same distance, and its initial, sorry, that should be a plus right there. If you plot those, let's just kind of take a look at this, you would see that you've got a different rate, right? A different rate for each company. So that's the slope. Here's the independent variable, and then the cost, right, is the dependent variable, right? The cost in dollars. And so on this plot, we've got two different lines. We've got one for K and one for D. So initially, when you have a distance of 0, right, the K company costs more. It's going to be 20 versus 16. But as you add miles, right, then K decreases and M increases because of the rate involved. So to find that intersection at crossover, we're going to set those two functions equal to each other. Right? So go ahead and do that. Right? That would tell us when they cost exactly the same. And then beyond that point, we would see that K becomes smaller. So this is just an example of using a graph to try and explore the functions that we see. And then it's just math right here to go ahead and kind of nicely solve for 100 miles. So this next one is very similar to the previous one. So I'm going to go a little bit faster. We're going to do it a little bit more just with identifying. So when hired at a new job selling jewelry, you're given two pay options. Pay would be an output. That's something that gets put in your hand. So we've got two, option A and option B. And so there's a base salary for each and a commission on your sales. So selling jewelry, right? Selling jewelry is the dependent, like that's the input, like that's the unknown, that's the input that we're going to need to then compare payment options. Right? How much jewelry would you need to sell? So in just a minute, you'll see I ended up calling that J. You could have called it anything you wanted. You could have called it S. You could have called it Christmas trees. It's just the variable. And so let's see how we can attack this. It'll be very similar to the last one. So there's my variable. I called it J. That's jewelry sold in dollars. It's the amount, and we say amount not like how many pounds of jewelry or number, but it has to do with how much money is made on those transactions. So here's our two functions. I'm going to call it OA for option A. That was 17,000 plus a 12% commission, and that 12% commission works on J, the amount that's sold. Option B is going to be 20,000 plus 5% commission. So if we just plot these, right, and just kind of get a feel for it. So when J equals 0, right, option A, you start with 17,000. Option B, you start with 20. So that was what this would represent, and that would represent, that's for A, this would be 17,000, that would be 20,000. And then the rate changes, right? The slope for option A is steeper than for option B. So at some point they're going to cross each other. And then option A becomes a better decision. Right? It'll pay out more, all dependent upon the amount of money in the transaction. So we just set those two equal to each other, solve for J, and where J is the amount of money. So there's just OA. Right? I don't plug in an independent variable. It's just the function, right, that we wrote right here. It's that function and that function are what we equate to each other, solving for the option. So I have one, actually do two more and deal with some shapes, some geometry. So you'll kind of see that on your You'll see that on your homework. Similar triangles might come up here. Not in this problem. Here we're just dealing with a rectangular box. Right? That rectangular box is, we have a square bottom, and it is 4 centimeters taller than it is wide. So we'll have a sketch here in just a second. But we've got a rectangular box. Let me do a quick one right here. There's the bottom, that's a square, and then up. So I'm looking at it as if you can see all the way through it here. And then up is that right there is going to be 4 more than what we see on the bottom down there. And both on the bottom are the same. So we're going to find the volume for part A, the surface area for part B. Those are all going to be a function of this unknown width. Right? The width, we'll define some variables down here in just a second. We'll call it a length and a width down there. For a square, they're the same. And then that'll be the height. And then we'll go ahead and solve for part C. It says if the box has a width, right? If it has a known value for the width, what is the volume in the surface area? So if you kind of think about that, what we're going to do is take our answer for A and B, which are going to be a function of the width, which we'll call x here in just a second, and then we're just going to plug it in and get an answer out. So the variable for our problem, we're going to call it x. It has units of centimeters, right? That is going to be, because it's a square bottom, right? That's going to be the length and the width that we find at the bottom. So here's a little picture down there. If we find it at the bottom, it's also going to be at the top. So it's an x by x square, top and bottom. The height, I'm going to call that h, is going to be x plus 4 centimeters. And we were told that in the problem statement. So the volume, right? The volume is just length times width times height. Right? That'd be for a cube. The volume. Think of it as the volume, the volume here, the area here, times the height. So we take that area and we just stack it a height number of times, and that's why we would multiply by the height. So volume, length times width times height for a cube. Right? Length is x, width is x, height is x plus 4. And so we end up with x squared times x plus 4. If we multiply it out again, we would have x to the third plus 4, and just keeping in mind this is centimeters. That's the units attached to the 4 right there. So the units on x, right, as we defined here, the units of x have to be centimeters for this to work. It would not work if you tried to plug in inches or meters here, because it wouldn't match the constant term that shows up, which is in units of centimeters. Surface area is going to be the area of the top, right, and the area of the bottom. So we've got twice the top and bottom, and then we've got 4 sides. And those sides would be x times x plus 4. And we've got 4 of them. So we've just got a little bit of math to do, and then we end up with a function down there. So that would be our surface area function. So the surface area is equal to this equation. All we need is the value of x. So same thing up here. The independent variable, right, the input variable is x. Same thing here. And we're going to get a different output, most likely. Here we get volume, right? Well, we get a different quantity, but number-wise, I mean, they could be the same, but they would have different units. So we'll keep that in mind. And so to finish, all we do is just plug in. We just plug in our values. So plug in 7 and go ahead and calculate it. Go ahead and plug in 7 for the surface area. Go ahead and calculate it. This would end up with centimeters, the answer here. Centimeters to the third, that's volume. Area has units of length squared, and that's what we would get. We would end up with centimeters squared. I missed my C right there. We'd end up with centimeters to the third for volume. So one little hidden nugget here, you'll end up with opportunity with similar triangles on your homework. And so as long as, right, if we've lined our triangles with the common angle, right, in the same location, then we just use a ratio here. Now we could use a ratio of any two sides, but the height and the length over here, the ratio of those two has to be equal to the ratio of height and length in triangle 2. So they might be the same, but we do know that the ratio has to be the same. They have to be ratioed, and if they are, then they're similar triangles. So when you have a problem that you know you have similar triangles, this is what you're going to want to set up for. And this equation right here, just keep in mind, that's only one equation. So you're going to be able to solve for one unknown on it. So you're going to need, if that's your only equation, then you're going to have to know 3 of those things to make that something you can get an output for. So our last one here, we've certainly done plenty. Consider 3 consecutive positive integers. Their product is exactly 2408 times larger than the middle number. What are the 3 integers? So 3 consecutive positive integers, their product is exactly 2408 times larger than the middle number. So we've got a relationship between these 3 consecutive positive integers. We just don't know what those integers are, but we're asked to find what those integers are. So let's go see if we can break this down. Let's let x be the smallest integer. So that would be our input. When we take the smallest integer and multiply it by the next integer, would be +1 away. The next integer would be +2, so that would be the product of 3 integers. We get, the output is 24, oops, I did that wrong, didn't I? You know what, this is wrong. Sorry, a little slight error there. That's 24, this should be 2400, not 2408. So, and so we see at this point you'd kind of want to take a break, just take a quick breath, come back to it. So what does our equation tell us? Number, next number, next number, all multiplied together. That's got to equal 2400 times the middle number, which is x plus 1. So this is kind of slick. Cancels. And we end up with x times x plus 2 equals 2400. So we end up with a quadratic. So now we're right back into that toolbox of, well, that's why it was so important to solve something like that. And so we can solve it by factoring. So you could use a number of different techniques. I just knew that 50 times 48 is equal to 2400. So I get 2 factors. I get an answer that's -50 and +48. And I know that I'm looking for positive numbers. So that's my answer I'm going to choose. And x plus 1 then is 49. X plus 2 is 50. So at this point you want to go and check. Go ahead and plug that in there. Take 48 times 49 times 50. Do you get 2400 times 49? And you will. So when I check that, I get 117,600 when I multiply 48, 49, and 50. And I get the same answer when I multiply 49 times 2400. So there's my check.